Okay, welcome everybody. So thank you for joining the first Distinguished Seminar Series, the CCMA Distinguished Seminar Series of the Civil Environmental Engineering for the spring term. So a few sort of housekeeping notes for all the talks of this spring, including this one. You will find the videos, if you are interested, at the website dss.mit.edu. So feel free to go there and to reach out if you have questions, if you don't find anything on that website. All right, so the series will have 5 talks for this term with a high prevalence of fluid dynamics of all sorts of scales and some transportation as well. And for the talk of today, our speaker is Professor Jeff Koseff from Stanford. Jeff Koseff is the William Alden and Martha Campbell Professor of Engineering in the Stanford Department of Civil and Environmental Engineering, and the founding Perry McCarthy Director of the Stanford Wood Institute for the Environment. Professor Koseff's research in environmental fluid mechanics focuses on the interaction between physical and biological systems in natural aquatic environments, including turbulence, internal wave dynamics and stratified flows, sea grass canopy hydrodynamics, and the transport of marine microplastics. Professor Koseff served as director of the Stanford Environmental Fluid Mechanics Laboratory, as chair of the Department of Civil Environmental Engineering, as senior associate dean of the School of Engineering in Stanford, and as member of the Provost Committee for the Environment. He also founded and was director of the Woods Institute. He's the recipient of numerous awards and recognitions, including the Knapp Award in Fluids Engineering from the American Society of Mechanical Engineering, the Stanford School of Engineering Tau Beta Pi and ASU Outstanding Teaching Awards. He's also Fellow of the American Physical Society and the recipient of the Richard Lemon Award, the inaugural Stanford Sustainability Award for his contributions to increasing the sustainability of Stanford practices and facilities. So without further ado, let me welcome our speakers of today, Professor Koseff.
Well, thank you very much, Lydia, and it's a great pleasure to be here. It's always a great pleasure to be in Boston and to be at MIT. And I was horrified that I went and looked in preparing this talk, and the last time I talked at MIT was 10 years ago. So it's amazing how quickly time goes, but it's great to be here, and it's particularly wonderful to be here to talk in a seminar that honors C.C. May, who many of us, even at Stanford, look up to as one of the great intellects of environmental fluid mechanics. Okay, so I'm going to talk today about the interaction between gravity currents and breaking internal waves. And this is a collaboration essentially between multiple people. At Stanford, Nick Willett is a faculty member, and Nick and I are essentially the PIs on this project. We had a postdoc, Charlie Hogg, who's some of his work I'll show, who did some of the early work. And then Yuki Tanimoto, who's a student, and there's Yuki on the left. He's a student who does all the work, of course. Now, we also had a visitor a year or so ago from UC Santa Barbara, Eckhard Mayberg, who some of you may know. And Eckhard became very interested in this problem. And his graduate student, Raphael Ouillon, who's shown over there, also became very interested. And they collaborated with us. So they did some of the numerical work. So what I'm going to show you today is essentially 2 experiments, 2 experimental setups, and also some numerical work that sort of goes in tandem with one of the experimental setups. So that's what I hope to do today. And so fundamentally, the basic question that we set out to answer is, how does an internal wave at a density interface modify the flow of an inclined gravity current which passes through the interface in a 2-layer ambient environment? So that's essentially the fundamental basic question. And you might think about, well, how did you get to this question? What motivated you to even think about that? And so I'll spend a few minutes talking about that, because I think it's important to understand the relevance of this to the near coastal ocean, and in fact to perhaps lakes and reservoirs as well. So the fundamental background you can think of, how do you get dense canopy, how do you get dense gravity currents? Here's an example of a lake or a reservoir where you have perhaps a cold flow, perhaps a sediment laden flow, perhaps a cold or sediment laden, typically in terrestrial environment. River flowing into a terminal lake where it will have initial momentum. It'll push its way out into the environment, into the lake, and at some point it'll plunge downwards where the density difference will determine that it goes downwards. So you have this downwelling region there, you have a plunge point, and so the flow will continue as a gravity current along the bottom. At some point, that gravity current will will mix with the ambient, and so depending on this topography, it might lift off the bottom and insert itself at some point in the reservoir. But obviously, from a reservoir, if you're interested in being able to predict the structure, the vertical structure of the reservoir in terms of its density, knowing where and when this dense interflow inserts itself is really important. So that's one example of a gravity current that we can think about relevant to the kinds of flows we're interested in. The other would be in the near coastal ocean, and it's more and more prevalent now, especially in California, where we do have water shortages, and not from time to time, more often than not. And so more and more communities in the near coastal ocean environment in California are thinking about desal as the great salvation. And so the thing with desal, of course, people have called it the drought-proof technology and things like that. There's a cost, an environmental cost, that we haven't really paid much attention to, and that comes from the fact that the brine, which is often as much as 20 or 30 parts per thousand in salinity higher than the ambient environment, the brine has to be discharged back to the ocean. If you do it in a very non-sophisticated way, and this tends to be what they do in the Mediterranean environments and in the Middle East, they'll just simply take that brine and dump it out on the beach and let it run down as a gravity current. Sometimes you get a little bit more sophisticated, like in San Diego, this recently commissioned Poseidon plant, where they actually have a diffuser designed in the classic civil engineering fashion. A lot of work done at MIT on these diffusers, a lot of work done by Norman Brooks and his cohort at Caltech, a lot of work done in Australia by David Wilkinson and others. But even if you design these diffusers, the salinity of the fluid coming out at the end, after all the dilution and the entrainment and stuff, could still be as much as 2 parts per thousand above the ambient, which doesn't sound like a lot, but it is enough to resettle and flow along the bottom. And there's pretty much no energy in the ocean at that depth that is going to mix it. So you get these very, very persistent brine pools forming at the bottom of the ocean. And if you're a benthic dweller and you depend on your livelihood is earned at the bottom of the ocean, that's probably not a pleasant thing. So it could have big environmental consequences. And recently, very recently, this plant here in San Diego, the one that I was talking to, was the subject of a paper published in Water. This is less than a month ago by Karen Peterson and her colleagues, including Adina Payton, who's at UC Santa Cruz. They went and they measured the performance of this outfall, this engineering-designed outfall, to see how it performed. And so pretty much the way this plant works, it's a co-located power plant and reverse osmosis desal plant, where they essentially take the outflow from the power plant, put it through reverse osmosis. Here's the brine, there's the potable water. They pre-mix the brine with the outfall again, and then put it back into the ocean. So when it goes into the ocean, the idea was that by pre-mixing it with the power plant out, that this initial concentration would only be 5-6 parts per thousand above the ambient, and then they would rely on dilution to take care of the rest. That's the engineering design. Unfortunately, when they went and looked at the performance of it, they found that the salinity was 2.7 units above ambient rather than 2. So this plant clearly was failing. It wasn't doing what it was designed to do. And the sort of the physics that I talked about before, where this persistent brine gravity current seemed to be in place still, despite the fact that it was coming out of this engineered diffuser and mixing, et cetera, et cetera. So it's clearly a problem. And if something that's designed to best engineering standards is failing, then it's obvious we have to think about another way of where we site and where we put these desal plants, if in fact that's what we're going to do. So one of the other things they looked at, interestingly enough, is they looked at the wave climate in that area, and they decided that the wave climate was pretty vigorous, but despite the fact that the wave climate was pretty vigorous, it didn't have much effect on the mixing of the gravity current. Well, surprise, surprise, why would it? I mean, we're talking about a surface phenomena that's certainly not going to have effects at great depth. So the question is, if you're trying to mix this brine outfall, what is available, what physical entity could be available to give you the kind of energy that you need to be able to mix the brine? And so we thought about this, and one of the things we thought about was, the only thing I could think of were internal waves that typically would ride along the density interface. When they get to the coastal environment, they break, they release enormous amounts of energy, and that energy then is transported back into the interior of the ocean, where people think that's the source of energy that will actually mix plankton, mix oxygen, mix sediments and stuff. So the question then arose, okay, can we set up a little toy problem, a nice idealized problem where we can look at the interaction then between a breaking internal wave and a gravity current to see even what likely will happen. So interestingly enough, the authors concluded in their study, we recommend all future desalination facilities be designed with optimal designed options of either diffuser systems or a higher dilution of the brine prior to discharge. Nowhere is it said maybe they should be discharged in places where the internal wave climate is favorable to some vigorous mixing. So that's the thing that we'd like to add. I don't want to put too strong a spin on that whole thing. That is a connection. It's not the only connection to this work. It's not the primary reason necessarily for doing this work. I think it's an interesting, more at this point, sort of an interesting theoretical problem. Obviously, you can think about all kinds of reasons why you can't necessarily rely on internal waves to mix things up. They're intermittent. They don't always occur when you want them to occur. They're not constant in time, et cetera, et cetera. It's not like you have this constant source of energy. However, just from a feasibility point of view, it would be interesting to see what would happen. So that's what I'm going to talk about today. If anyone has any questions, then feel free to ask at any time, interrupt, no problem. This is also data, just to finish this point, taken in the Middle East. We're not allowed to disclose where, but as you can see, it's not in a very deep environment, and you can see this is salinity, and there's this persistent salinity wedge offshore right opposite a desal plant. So this kind of structure is very stable, very persistent, and very problematic. If you're benthos, if you're a benthic dweller living down there, and you're sensitive to the ambient salinity levels. So we can take that question that I posed at the beginning, and we can recast it a little bit. Specifically, how is the downslope mass flux influenced by the interaction between the interfacial wave and the current? So let's think about it in practical engineering terms. In practical engineering terms, the thing that I want to do is disrupt the gravity current. I want to reduce the downward mass flux. That's what I want to do. So how is that actually reduced as a result of the interaction? So we can cast the problem in a more practical way. So what are the basic elements of the flow that we're going to look at? The first is the gravity current. This is work done by Paul Linden and his colleagues at Cambridge, just sort of showing a gravity current. This particular one was not on a slope. This comes from a lock release where you have fluid of different densities on either side of the lock. You raise the lock and you get this exchange. But you get this gravity current, which typically has this head and behind it, there's sort of an oscillating interface that has strong vortical structures which evolve as you move downstream. And depending on the density difference driving it, you can predict, the velocity of this gravity current is quite predictable from essentially the density difference and how it modifies gravity times the depth of the opening of the lock. So it's very well characterized. We know what gravity currents look like. You put them on a slope. They have similar characteristics. And so that's essentially what they look like. You see them in nature as well. Here's a gravity current called a haboob, which is produced as a result of a strong downdraft from a thunderstorm. You get this very strong cold air downdraft, blasts into the ground, stirs up all the sediment, and then flows out. That jet flows out, or that current flows out over the land. Not a very pleasant thing to be caught in, unless you like having a mouthful of sand. Okay, so that's gravity current. And you can see they occur on very different scales in very different ways. Same phenomena, though. So what happens if a gravity current enters, let's take it one step further, if a gravity current enters not a uniform density and ambient environment, but say an ambient environment that has a two-layer with an interface, so some kind of thermocline. So we've got warm water overlying cold fluid with some kind of interfacial thermocline zone. What happens then? Well, the study was done by Cortez et al. In 2014. And basically what they said is if this is rho 1, this is rho 2, and the initial density of the gravity current is rho 3, then you can have three possible outcomes. There are three possible outcomes if this happens. The first is that rho 3 is pretty close to rho 1 or rho 2, and so it'll just insert itself at the interface as an interflow. That can happen even if rho 3 is greater than both of them. As a result of mixing, you get mixing going down the slope, rho 3 will be modified by entrainment of rho 1. So it might be modified to the point where you simply get an insertion at the interface, and that's called an interflow. Or it could be that rho 3 is so large that it just punches its way clear through the interface and inserts itself. Even though there is mixing as it goes down, there's still density of rho 3 is still much greater than rho 2 and rho 1, and the gravity current will insert itself at the bottom. We call that an underflow, pure underflow. And there could be a rho 3 which results in a split flow where you have some of the fluid going into the interface and some of the fluid going as an underflow. Now, obviously, from an engineering point of view, if you're looking from a point of view of managing the outflow of this desal plant or whatever it is, or even a lake or reservoir, you're interested in knowing what goes to the bottom, what goes to the interface, and how much of that. Because if your predictive requirement is what is the temperature structure or what is the density structure of the receiving waters at any time, this kind of information is really important. So you want to be able to characterize that. So this was done by Cortez et al., and this is what they show. I want you to remember this because it's going to be important. And you can characterize this gravity current by a Richardson number, which, as you all know, is the ratio of buoyancy to shear forces. So depending on how strong the buoyancy is, you'll either get pure underflow, split flow, or you'll get an interflow. All right. Now, what about the other basic element of the flow? The other basic element of the flow are internal waves. So this is a side scatter radar image in the near coastal ocean. You can see there's a density interface right here, and on that density interface, from the particles in the flow, you can get an image of what's going on, and you can see this internal wave riding along this interface, and it seems to be growing a little bit as it gets closer to the shore, and at some point it grows quite dramatically. It starts shoaling, and then it breaks, and then you get this run up the shore, which we call a bolus running up the shore. This is actually a fairly common phenomenon in Monterey Bay, for example. You get that. This region here where the wave actually breaks, this is where you have a source of great turbulent kinetic energy that can actually then be transported back internally into the flow, and it can be used for mixing a lot of scalar quantities. But this is basically the shoreward transport is dominated then by this braking event and then this upward bolus running up the slope. And we've seen in Monterey Bay, actually, this is a very efficient way. Depending on how vigorous this is, you can actually connect the very deep canyon water, which has very high density, with the shallow water, where they're delicate in sort of kelp forests and stuff like that. This mechanism is a very efficient way of connecting this water body with this water body over here by bringing this bolus up. So it's important. It has strong environmental implications. So this whole thing we can characterize by a Froude number, which is the ratio of inertia to gravity forces. And in this case, gravity is the modified gravity because of the density difference. So that's the basic elements of the flow. You've seen the gravity current, and then you've gravity flow, and then you've seen this is what the Scholling internal wave looks like. Now, we've done quite a bit of work, which is why I was attracted to this problem as well, on Scholling internal waves. We'd spent quite a bit of time in the past doing lab experiments. And if you're interested, it's in this paper by Christine Moore and JFM in 2016, looking at the characteristics of Scholling internal waves. The wave would be coming from here. It would be breaking, in this particular case, somewhere over here. And here's the bolus running up. And I'm going to show you a sequence here. I'm going to show you a video here where there's a sequence of waves arriving, each one with progressively larger amplitude. And you can see what happens. When we talk about a Scholling internal wave and wave breaking, what I want to show you is not all internal wave breaking is the same. So it's important to be able to characterize, I need to find where there it is. So here, let's watch. There's the first one, getting bigger. There's the second one, breaking, sending that surge up. Here comes the third one, breaking. Fourth one, still. Yeah, whoa, there's one that you would sort of think of, and the next one. So what you basically saw there were at least 3 or 4 different kinds of breaking events. So even though the wave was breaking, by our definition of breaking, not all the breaking looked the same, okay? Now, I could play that again. Do you want to see that again? Yes, you do. Of course you want to see that again. What a stupid question. So you play that again. So there you are, small waves breaking. You get these events, the bolus running up the slope. Just look at the nature of the vorticity in there. Oh, still looks like it's rotating. There's one breaking forward, and the next one breaking forward as well. So we spent a lot of time looking at those Scholling internal waves by varying the characteristics of the oncoming wave, essentially by varying the Froude number. And what we found was you get 4 different types. You get 4 different types depending on the nature, the magnitude of the oncoming Froude number. You get one where the breaking is actually backwards, not forwards. We call that backward breaking. You get a top breaking one, which forms then a turbulent bolus, and then you get a top breaking one where you don't even form a bolus. You just get so much mixing that there's just a sort of a surgy mess, and then you get forward breaking. So this is the backward breaking that I was talking about. You can see as the wave is about to break, it actually starts breaking forward, and then it flips around and actually breaks backwards like that. So backward breaking. Not something you typically see in surface waves. Most surface waves that you're familiar with, you'll see forward breaking, right? When you go to the beach, you don't see too many waves breaking backwards. However, think about it. If the wind is really blowing strong offshore, I've seen this, as the wave's about to break, it can flip it over and break it the other way. So that implies if the shear in the water column is right, you can get that. So that's the backward breaking. Here's the forward breaking, looks classic. The classic forward breaking. By the way, these images were done with planar laser-induced fluorescence with correction for index of refraction matching. That's why they look so nice and clean. Yeah, it's a lot of hard work. And this is what happens when you get even more. This is what I'm talking about, the braking. Here you won't even form the bolus. You'll just get this very turbulent mess, and then you just sort of get the surge. You don't get a bolus going up there. And then top braking looks like this, where it actually brakes right there. And if it gets a little bit more vigorous, again, you result in turbulence. So this is not the point of what I'm trying to say. I'm just trying to say that we have pretty good evidence of what these braking internal waves could look like out in the ocean. It's a lot harder to characterize them like this in the ocean because you can't see them. But at least we understand that the Froude number does play a part in sort of setting the conditions then for the kind of braking that you're going to get. Okay, so what you came to see, though, was not that. What you came to see was this, right? What happens when you have a gravity current meeting oncoming internal waves? So that's what I want to talk about now. Okay, so let's put the whole thing together and do these experiments. So here's the experimental setup. It's quite simple, actually. And one thing I've learned in 36 years of doing this stuff is that the simpler the experiment, the better. The less sophisticated the instrumentation you have to use for your students, the better off you are. When you have to use the most sophisticated 3D PLF to get small incremental results, you're not in a good space, okay? So I learned dye, just basic food dye, can be your best friend. All right, Alex probably hates me now, but it's okay. All right. What's that? No, we only used 3. All right, so here we have the reservoir holding fluid of density rho 3, appropriate color, red, right, for Stanford, blue for Berkeley. We always red above blue, very important. We can do laser-induced fluorescence. We can do planar laser-induced fluorescence as well, so that's why the scanning mirror is there with the laser. We have a conductivity temperature probe if we want to actually get some hard numbers out of it. But what I want to just show you now is qualitatively a little bit. We can control the depth of the upper layer, H1, the lower layer, H2, and we can control the inclination angle. For the experiments I'm going to show you today, that's a constant, that's constant, that's constant, constant, constant. That's the only thing that we're going to vary. And we also varied H0, the amount that we opened the lock. Those are the things that we varied. Okay, so we open it. Depending on rho 3, you get a gravity current coming down. There'll be entrainment along this interface, which will change the density. So the density of the fluid going into rho 2 is going to not be quite the same as rho 3. So we need to characterize and measure the density there. But then the fluid goes into the lower layer. Okay. So you can characterize this gravity current, as we said, with a Richardson number. And you can see the Richardson number here. The important parameters are the difference between rho 1 and rho 2, and the buoyancy flux that's due to this gravity current. And the buoyancy flux will also depend on the density difference between rho 3 and rho 1. It'll depend on the velocity of this current, and which will set the flow rate, and also, obviously, the width of the channel. So all those can be calculated. These are all parameters that are used typically in the literature. This is a definition due to Wells and Wetlau some time back. Okay, so that's what we're going to do. And so here we go. Here's 3 simultaneously for you, 3 different experiments. 8.1, okay? 3.7, 2.3. So think about, if we go back just quickly, just to remind yourself, the smaller the Richardson number, the bigger the buoyancy flux is going down, which means you can think about that being the stronger the gravity current is, okay? The more punchy, I like to call it. So if you had to lay some bets, if you laid bets, we've got Richardson number of 2.3, we've got Richardson number of 8.1. If you laid bets, your bets would be, smart bet would say, 2.3 goes to the bottom as an underflow, 8.7 goes as maybe an interflow, and the one in between goes as a mixed, okay? That would be the smart money. All right, so let's see what happens. Everybody okay with that, right? Because that's what the Richardson number suggests. And you guys, you're smiling because you know you're being set up. All right, here we go. Here we go. Here we go. That's real time, by the way. Oh, here we go. 8.1 looks like an interflow. Yes. 3.7 looks like a mixed. Yes. And 2.3 looks like a strong underflow. Yes, but not quite. What do you notice that's a little different from the Cortez et al. Characterization? What's different here? If you said they all look like a mixed interflow, underflow, you're correct. That's the correct answer. There isn't a pure underflow. There isn't a pure interflow. Every single case we ran, and I'm just showing you 3, no matter how low we made the Richards number, there was always an interflow. And no matter how large we made the Richards number, there was always a little bit of an underflow. In some cases, the underflow dominated, like in this case, and in some cases, the interflow dominated. That was good. Okay. Now, there's no oncoming wave here. This is just purely into an ambient environment. Okay. We needed to be able to do this first. But I want you to notice something about the interface as the wave goes through. All right. You can see right there, there's a wave, right? And there's a wave that seems to be somehow tracking this gravity current as it moves down. If you look up there, there also appears to be a wave, even though it has the gravity, there's a wave there. And so that's very interesting. So the surface is clearly being affected then by the gravity current itself. The gravity current itself, as it passes through the interface, as you would expect, and lifts the interface out, is creating a surface interfacial wave as well. Okay, it's creating one as well. And what we've been able to do is characterize that. I'll get to that in a second. So that's essentially what we've found, so far. But we can characterize we can do a little bit more with that. So what we can do is we can characterize the nature of the gravity current before it enters the lower layer. And then we can also characterize the gravity current as it goes into the lower layer. So here's some of the tools and some of the data you can see just so you can get an idea. What I've done is I've taken that and I've just rotated it so it looks horizontal, but it actually isn't. So this is planar laser-induced fluorescence, where we set up we interrogate these pixels, so these become essentially effectively our probes at these different levels, and you'll be able to see over here what the salinity looks like at these different levels. Here's the salinity versus time, and you'll be able to see how the salinity varies as this gravity current passes through those positions. And here it is, right there. As it passes through, you can see it goes up, and then this is what. So from this, we can get actually an indication of the height of the gravity current. We can get an indication. We can characterize the front of the gravity current. We can do all the kinds of things that we might be interested in. We also might be interested, obviously, in knowing what the speed of the gravity current is. So we've set up, in a similar way, we've set up a way of being able to, there it goes again, we've been able to do that. All right, so that gives you an idea of what the density structure looks like, and it's just playing out over here. All right, what about the speed, the gravity current head speed, which is well characterized in other work? We wanted to be able to see if we could use this technique to be able to do that. And you can see we get a very nice readout, and it's actually, as one would expect from what theory says, you can predict this, it's very nice and linear. So the speed of the gravity current before it hits the interface is pretty nice and linear. So that gives us a nice way of being able to characterize the buoyancy flux. So these are the kinds of measurements that we need in order to be able to calculate what the Richards numbers that I reported on the previous slide were. So this is the kind of stuff that you need in order to be able to do that. You need to know the density structure, you need to know the height of the front, you need to know the speed of the front. So that's all good. And there it is again, just in case you want to see. Okay. So watch this. I'll play it again. This is twice the speed now. Okay. And what we're seeing, let me just help you. What we're seeing is the middle case, right? The strongest case, the 2.3 case. And what we've done is this top image is 1/2 of the tank, and then it continues over here. So it's not 2 experiments. This needs to sort of be mapped over to there, but the screen's not big enough, so just showing it like that. I'll show it again. This is two times the speed. All right, we'll show it again. There it comes. Strong underflow, produces a wave. Here it comes over there. It looks like this wave is tracking that. But there comes the interflow afterwards, creating another wave behind it. So the actual interaction between the gravity current and the interface is going to be important to characterize because we haven't even talked about oncoming internal waves. But if the gravity current itself is setting up internal waves and there are oncoming internal waves, there'll be wave-wave interaction, which ultimately could be important. But you can see those are the two waves. So there's the one here, which is generated by this fluid apparently pushing that in front of it, and then this one over here, which is apparently the wave that was locked to the front of the gravity current. So we think there's two kinds of internal waves that are themselves generated by the gravity current, okay? The first one, for a dominant underflow, as you saw, leads to an internal wave that seems to be locked with the gravity current. That gravity current seems to be following the wave seems to be following the gravity current as it moves down the slope, locked in phase with it. And in many ways, you can think of it as the reverse Norwegian fjord captain's problem. You know, the Norwegian fjord captain goes over a density interface, right? As a result of moving, you create a wave at that interface, which is then following the boat and actually increases the drag. So these Norwegian fjord captains found that when the upper interface is pretty small and the interface is close to the surface, that the boats just wouldn't go as fast as they thought they should go because you're dragging this wave. So it's sort of locked. This is the inverse. This is where the gravity current now is producing the wave, and that wave is locked to it. All right? And then the dominant interflow, which was the second part, leads to an internal wave that seems to be launched in front of that interflow. So we differentiate between the waves. There's a locked wave and a launched wave. And the launched wave seems to be detached from the gravity current. The gravity current just set it up and launched it, but didn't lock it. So you should be able to analyze them, and you should be able to look at them. So there's the locked wave. There it is right there, following the gravity current, right? So the speed is set by the underflow. The wave crest is always behind the head. That's the locked one. And then the launched one, look right there. That's the launched wave right there. That was formed by that. So the speed is independent of the gravity current speed because it's moving away from it, but it was launched by that. So those are the two. So you should be able to quantify that using the Froude number, which is the appropriate dimensionless number for characterizing these internal waves. And so our hypothesis was that the Froude number, which is the gravity current speed divided by the internal wave speed, all right, that's the ratio there, should be 1 for the locked wave cases and less than 1 for the launched wave cases. That's the hypothesis. If it's truly locked, the Froude number should be 1 because it's moving together in lockstep. And if it's less than 1, then it's sort of moving away from the source. And so that's what we expect. We expect to find then that if we did that, and I'll just remind you then, we should be able to characterize it. So I'm just showing here a slightly different way of characterizing the gravity current using a Grashof number. But the Grashof number is related to the Richardson number. It includes H0, which is one of the things we varied. Here's the Froude number over here. So high values of Grashof number would be low values then of the Richardson number. So for the lower Grashof numbers or the higher Richardson numbers, we observe launched waves. Froude numbers less than 1. So here they are. This is low Grashof number, high Richardson number. Remember, high Richardson number, propensity to form interflows, which would then be launched waves. And so that seems to work pretty well. And then for the intermediate Grashof numbers, which are these, which would be then the lower Richardson numbers, you can see the Froude number plus or minus is around 1. So it looks like we've identified something that's reasonably important in terms of setting up how the gravity current itself can generate interfacial waves, never mind the oncoming interfacial wave. So for the last few minutes then, what I want to do is show you some of the preliminary work we've done. So we haven't done, this is as far as we've come with this experiment. It's just started, essentially. We haven't done seriously the oncoming internal wave in this facility. But we did initially, one last thing I'll show you from this that we could get is we want to be able to quantify the splitting of the flow. So we want to be able to say, can we come up with a method of quantifying the splitting of the flow? So if you take this, here's the initial profile, all right? And if it's this is what the final profile would look like. So for the experiment that I just showed you, this is what the final profile looks like in the tank, in the deeper part of the tank. So you can see some of the fluid went to the interface, some of the fluid went as an underflow. One little thing just to be aware of. Remember, you're adding mass into the tank. So this is not all interflow fluid. As a result of putting mass in the bottom part of the tank, you're lifting the whole profile up. So you've got to be careful. Don't attribute all of this to interflow. Part of that is just simply the result of the fluid being inserted and lifting the profile up. That's what the actual final profile looks like, right? Now let's look at some theoretical ones. What if all the flow went to the bottom? A pure underflow. That's what the profile would look like. You'd have this piece here due to the fact that you're lifting the whole fluid body, right? But here is what's important. You've got this right here. So this is what this, and you can calculate the center of mass of this distribution, the green distribution, and that will tell you what the center of mass of the final profile is if it's a no mixed underflow. If the underflow went into the lower layer and mixed itself completely, distributed itself completely in the lower layer, this is what the profile would look like, the purple. And you can calculate the center of mass of that. Okay? You can calculate the center of mass of that. And if it was a full interflow, this is what the profile would look like. That's where the fluid, none of it going in the lower layer, so the profile doesn't lift itself up, all of it over there. And you can calculate the center of mass of that. So by calculating the center of mass, essentially, and comparing it, say, to the no mix underflow case, you can get an idea of the relative amount of partitioning between the interflow and the underflow, and that's what we did. So what you do is you calculate the center of mass of the gravity current. So you calculate the density minus the ρ2, which is the density in the lower layer. And the center of mass then is just sort of taking the first moment over the 0th moment, and you can calculate of the distribution. You can calculate the center of mass. And then what we do, which is really important, is we normalize it by the maximum change. So the maximum difference you could get is if you have a full mixed underflow and a no mixed underflow. That's the maximum difference that you could get in the center of mass. So we normalize by that. And then the actual center of mass star we calculate by is this number minus the center of mass for a no mixed underflow. So when you do that, this is what you get. If you had a normalized center of mass, it should be 1 for a full mixed underflow and 0 for a no mixed underflow. By doing it that way, we've sort of bounded. So 0 would be a no mixed underflow, a pure underflow. 1 would be a full mixed underflow. And so we can see how the cases fall for the different Richardson numbers, how they fall between there. So you can see most of the cases are far from full mixed underflow. This is most of the cases that we ran. The center of mass is about 0.2 to 0.25, suggesting that you're falling closer to the no mixed underflow case than to the full mixed underflow case. That's for these Richardson numbers here. And for these Richardson numbers here, it's even higher, suggesting you're getting even closer to that no mixed underflow. But you can see there's no cases with 0, there's no cases with 1, as Cortez et al. Had sort of hypothesized. They're all mixed interflow cases, but just of different strength. So that's important. So I don't know how to extend the Richardson number range lower than we've got, but no matter what we do, we can't get a pure inner flow. No matter what we do, we can't get a pure underflow. And this can show you, for certain cases, we can get closer to a full mix underflow, and we can get closer to a no mix underflow, but we can't get the pure cases. All right, so you can see, even with strong underflow, there's always some interflow. That's the bottom line here. All right, we'll leave this one out. All right, so let me just focus then for the last few minutes then on some of the early experiments that we did and some of the numerical modeling where we actually looked at, I'll just give you a sort of a preview of what happens when a gravity current does actually interact with an internal wave. And to do that, we had a much smaller experiment. This is the beauty of just trying something quick and dirty. This thing here is about 1.5 meters in length. It's basically a nice little teaching tank that we used. And we had an idea, just tip it on its side, just create a slope, put a lock there, and we can look at this. So we've got fluid of row 3 over there. We've got fluid row 2 over there, row 1 over there. You basically just raise the fluid level behind the lock an amount A. The lock length is L. And you can show that the Froude number for this particular of the wave coming out of here, if you pull this up, you'll generate a wave. You can see because of this fluid that's blocked there behind there, that the Froude number is actually A over L. You can show that very nicely. And it's a nice little scaling thing. So all we have to do in this experiment then is we keep row 1 the same, we keep row 2 the same, we keep row 3 the same. All we did was we varied A. That's it. We just varied A, and we let the gravity current come running down, varied A with different oncoming internal waves, and we wanted to see what would happen. So these are small experiments. They're not easy to visualize, so I'm going to apologize for the visualization quantity. But this is the contribution from Santa Barbara. I don't expect you to read all that. But we did essentially 3D incompressible Navier-Stokes simulations of that 1.5 meter long tank. So that's the nice thing about using small tanks. You can do simulations of them. And essentially using enough grid points to have a quasi-direct simulation. And if you're interested in the characteristics of the numerical method, which was developed by Eckhart Mayberg at Santa Barbara, that's right there. All right, so as I said, the wave Froude number is simply A over L. We varied it from 0 to 0.29, and we kept the gravity current Richardson number constant at 3.9. So we fixed the gravity current, and we said, all right, what happens when waves of different amplitude interact with that gravity current? All right, everybody okay with that? So here we go. First, we do a no wave case. So let's see what it looks like with no waves, just to be. Now, what I'm going to show you, if you look here, this is a very cheap sort of pliff of the flow as the gravity current enters. So when it enters AA, that's about this point over here. And watch what happens in there. All right? So here we go. There it comes. It comes in there, lifts it up. There's sort of it slows down for a little while, and then it punches its way through, but keeps going on its merry way. There's a little bit of mixing there, but you can see the gravity current goes through. That's with no wave. All right? Now let's put a wave. Here we go. Let's put a wave. So the wave is going to come from here. So you watch this region over here. That'll generate the wave. Now we have a look what happens. Here comes the gravity current. It enters right there. Here comes the wave now. Here comes the wave. Boom. It looks like it just chewed off a whole big part of the gravity current. Some of it continued, but it kind of completely stalled out over there and mixed it out. So it definitely had an effect on the gravity current, I would conclude. All right? Definitely did. So here's summarized sort of what it looks like. We call it the decapitation process. So here's the no wave case. Here comes the gravity current, lifts up the interface. But after a little initial interaction, it just continues to flow down, and that's it. However, if you looked at those images, we just pulled images out and put a little false color in them. That's what the 0.29 case looks like. So you can see, here comes it comes in. Here's the wave coming. Look over there. There's definitely an interaction. There's a lot of blue fluid, which is mixed fluid, above the gravity current. And this whole bit of fluid then is going to get pushed back upstream. So this is the decapitated fluid. You've essentially decapitated the gravity current head. Okay, sorry for the gruesome image, but The reviewers loved that terminology, so we went with it. All right? Okay, so you say, that's terrific. Did it result in a mass flux change? Remember, the problem was, will that actually reduce the mass flux? So we can calculate the mass flux. You can estimate the speed of the gravity current. There's the angle of the inclination, and then you integrate the PLIF images from 0 to the height of the height of the free surface, all the way up, CDH prime, and you can get an estimate then of the mass flux. Okay, and here we are. So here are the mass fluxes estimated passing through that in AA, that plane AA in the experiment. So here we go. No wave case. This is the no wave case. So there's initially a high, and then it drops off as the gravity current peters out, obviously. Here's a wave of Froude number 0.14. You can see it doesn't get as high. And here's the Froude number of 0.29. Doesn't get as high yet. So it looks like, yeah, something is definitely happening. The interface, the wave definitely seems to be having an effect, a strong effect then on the mass flux. Well, you go, that looks pretty noisy. How repeatable is that? Of course you can ask that. So we go, that's it. So we do it 3 times just to see. So this is 3 times Froude number of 0.29. There's 1, 2, 3. And of course the differences, but you can see there's strong similarities in terms of magnitudes as well. So it's fairly repeatable. It seems to be a fairly robust result. So you can calculate that then, and you can then plot what the mass flux is as a function of the Froude number. And this is the normalized mass flux. We just normalized it over here, so you can get a nice relative. So this is the no wave case. This is the Froude number of 0.2, and you can see between that case and that case, there's about a 40% reduction in the mass flux. So clearly, just a small, not a particularly huge wave can actually, through this decapitation process, it can reduce the mass flux going down the slope. All right, so you go. That's about the limit of what you can do with this experiment. But the numerics give you a lot of advantages because I can compute all kinds of things with the numerics. And I might ask, how efficient is this mixing? How much mixing actually does occur? Yes, I can see the mass flux goes down, but how much mixing actually occurred? So you can do that from the numerical simulation. So here's the numerical simulation. There's the row 3 fluid. It looks like the experiment, right, the initial setup. And that's how we set up the initial condition for the numerical simulation. This has a Froude number of 0.22. So you should see a wave coming this way. You should see a gravity current coming that way. And then the color of the fluid will tell you how much mixing actually occurred. That's nice. Whoops, I should show you it, right? Where is it? Oh my God. There we go. There it comes. There it comes. There comes the internal wave, a little bit of instability on it. Enters, enters, enters. And you can see changing in color, mixing occurring. You can see the decapitation process and the stuff being pushed back upstream. So it has a lot of the same. It's not exactly the same as the experiment, but it has very similar elements to it. So you don't have to say it's an exact replica, but it's, you know, it's a pretty good. So the question now you can ask with the power of numerical methods is, I'm interested in how much difference there is between the wave and the no wave case. So you know what you can do? You've got the no wave simulation, you've got the wave simulation. You've got them exactly matched in time, because that's what you can do with numerics. Why don't you just subtract the density fields between the two and look at the difference over time, right? So you should be able to see differences. And one of the differences you should see is you should see the region where the decapitation occurred. And for the no wave case, you should see the region where the gravity current continued to flow underneath and punch its way through. So that's what we tried. So this, what I'm going to show you now, is a visualization of the difference between the two simulations. Instantaneous differences in concentration between the no wave case and the wave case. So here we go. All right. That point is where the gravity current will enter the picnic line. Now you can see there are little bits of differences, but they're not. The differences are blue. It would be Yellow would be present in the wave case, blue but it would be present in the no wave case. So there it is. This fluid here, was only present in the wave case, but not in the no wave case. This fluid over here that was mixed. And this fluid over here, which is the gravity current continuing to flow, was only present in the no wave case, but not in the mixed case. So this shows you brilliantly, very quickly, the differences between the two. That's really cool. How much difference does it make? To look at that, we borrowed this technique from Winters et al., which is really nice. And it's essentially looking at the PDF of the background potential energy, which is the amount of energy that exists in a tank once this irreversible mixing has occurred. So this is the product of irreversible mixing, the change in background potential energy. Think about it this way. Let's say I have a tank that looks like, with a density that looks like that, initially, at T equals 0. Well, you can now count up all the sections that have certain densities, and you'll see that the PDF would have, most of the density would be predominantly this and or that. And there'd be a little bit of the stuff in between because there is a smooth gradient. All right? Now I'll take a turbulent eddy at that interface and I mix it up. So I resort it and I get now a final profile that looks like that. I can then calculate what the PDF of the density profile is. That's the background potential energy. That's the true mixing. And the difference between the two then represents how much true mixing actually occurred by subtracting the difference in the background potential energies. That is the way of looking at, that's as rigorous a way as you can look at to find what the true mixing is. All right, so in this particular case, I'll show you, I won't show you this one. I'll just go a little further. Here, I'll just show you here. This is Raphael calculated the difference in background potential energy at different times for the different Froude number waves minus the background due to the no wave case. So this actually represents the differences, and you can see if you follow this, the stronger the wave gets, the more mixing actually occurs. Actual mixing occurred, all right? So the waves not only reduce the mass flux, but they are apparently also increasing the amount of mixing that occurs, which is good. And this is a summary, as you can see, as a function of Froude number. You can see the higher the Froude number, the more mixing occurs between the no wave case, the wave case and the no wave case. This is great. You can look at that. That's one way to look at it. Another way to look at it is to look at the PDFs of the density, as I showed you before. Now I've just turned them 90 degrees. The red would be the initial, right? 0 would be, one fluid, and 1 would be the other fluid. This is for the no wave case, and you can see this is the product. This is as a result of, there's still mixing in the no wave case. You get a lot of intermediate densities being produced as a result of the mixing, even for the no wave case. But for the wave case, it looks different. And so, okay, it looks different. Can I take the difference between the two? Sure I can, and there it is. That's the difference between the two. So the difference between the no wave case, the wave case, and the no wave case is this. This is a big difference over here. That's a big difference over here. This is the fluid that continued to flow down the slope in the no wave case, right? This is the decapitated fluid right there. So you can even see, and this helps you identify, how much mixing occurred and what the different regions are. So there's the decapitated fluid right there, and I don't need to show you that again. So I'll just summarize quickly then. That's as far as we are in terms of the work. So we've characterized the gravity current by use of a Richardson number and a Grashof number, if you want, interchangeable. Interface intrusion always seems to occur in some manner. We're not getting a pure underflow. We're not getting a pure inner flow. We're always getting the mixed case, which is different from the Cortez result. Very interesting interactions between the gravity current and the pycnocline. You can see the pycnocline gets raised by the gravity current. There's a vortical structure that's set up behind the head of the gravity current, and there's interfacial waves that occur due to the gravity current flowing down itself and the interflow. So we found that as well. And we showed as well that the downslope mass flux reduces with increasing wave amplitude or wave Froude number. So we've actually demonstrated that. We've also demonstrated that there's irreversible mixing as a result of that. All right, so we've specifically the mass flux in the initial part of the gravity current is reduced by as much as 40% for the largest wave that we did. We also identified the decapitation mechanism, right? And then there's two papers. This one, which is in environmental fluid mechanics. This one essentially shows the results of the small-scale experiment that I just talked about. And this paper hopefully will come out pretty soon. That's the numerical simulations of that. The paper that describes the first set of experiments that I showed you is in preparation now. So hopefully that'll come out. So that's what it is. And the next steps then are to introduce braking interfacial waves in the larger tank, right? Measure the enhanced mixing and interface intrusion and observe the interaction between the gravity current and the braking internal wave. And just to whet your appetite, here is something very fresh and very new and not even analyzed yet, but here it comes. This is what you've been waiting for, so I will reward you. There it comes. There come the internal waves. There comes the gravity current. Punches its way through, and now, boom, it seems to slow up. Now watch what happens. A little bit out of view, of course, right there. Whoa, some interaction that's now completely stalled out the gravity current. Even though there's an intrusion there, this whole thing is now stalled out. So looks like it's going to be pretty interesting when we get to do it a little bit more. All right, you've been very patient and very kind, so thank you for your attention. And I am happy to take any questions. Thank you. Yeah.
So what happens if you vary the phase of the interaction between the gravity current and that one wave that you release? So
that's exactly that's the million-dollar question. That is actually a great question, because if I want to bring it back to the desal plant case, what you really want to look at is have a mature, developed gravity current that's running and hit it then with the internal wave. Phase is everything. But we absolutely have that in mind. That's absolutely where we're headed. That's the most important thing. This is not really, as somebody said, this is cute. It is cute. But it's not really relevant to the issue of desal plants. Well, desal plants are not everything, so yeah. But we have learned a lot, But you're right. What we will do now is we'll set up the tank in such a way where we could have the gravity current flowing for a minute or so. Can't have it much more than that because you don't want to fill the thing downstream. But that should be enough to hit it with about 8 or 10 internal waves and see what happens.
Yeah, I even think the leading edge of that plume hitting a different point, like.
Yeah, well, I think the thing is what happens when it breaks on the gravity current itself. So there's a nice flowing gravity current in that seems to be, one of the more interesting things. That could be very disruptive.
Yeah, you saw the water level lower as that wave comes in.
Yeah.
And it
changes. It's the phasing. Absolutely, Alex, you're right on the money with that question. Perfect. Yeah, Eric.
All your experiments were with discrete stratification. What happens if you have continuous stratification?
Yeah. So if you have continuous stratification and you want to make internal waves, as your colleague Tom Peacock can tell you, it's really difficult, right? So we have one of those wave makers with the sliding plates and stuff like that. It's not, the thing that Tom did that was so smart was that he has a racetrack type tank, right? So the internal, when you've got these plates sliding backwards, you're generating waves in both directions. So the waves that he doesn't care about sort of get dumped behind and go into a wave dump. We don't have that situation yet. So for us to do continuous stratification, we have to use a different wave maker. We can't use that. We have to use the different one. Here's the thing, though, and we're getting data for the near coastal ocean in California. You could argue, with a little couple of scotches in you, that the top layer is pretty well mixed, right? And the bottom layer of the near coastal ocean is pretty well mixed. And most of the density difference occurs in that thin interfacial layer. Now, there is some gradient in the top, but it's not like, the bottom is that strongly stratified. So it would be interesting, this is where we get critiqued, and and people say, how relevant is it? It's just a two-layer system. We can see generating internal waves we could probably put a little bit of a gradient in the bottom and still generate internal waves successfully using the wave maker, the oscillating wave maker we use. But if you wanted to have a strong stratification, you would need to use a different wave generator. And that's where we don't have the capacity to do that now. But that is a good question. That said, if we have a continuous stratification in the bottom versus not having one, I'm not sure that really changes the nature of the oncoming. I don't know how much it affects the nature of the oncoming internal wave. So I think our experiment for the moment is reasonable. But yeah, we could certainly, I take your point. And it's not easy to do. That's the answer. Mm.
Could you use numerical methods to have the continuous form of stratification? Just like compare it to
Yes.
numerical methods?
So that's where the numerics would have to be confined to a smaller tank, because to get the kind of resolution without having to resort to modeling and stuff. So I don't think we could do a 5-meter long tank numerically yet. But absolutely, that's where it's still tricky, though, to have the right boundary condition numerically to do internal waves in a continuous stratification. So, but that's been done, so we could easily borrow that. But that's a great question. Yeah, that's where numerical methods are used, are good. And so you use them in conjunction with the physical experiment. It's very powerful. Yeah, Eric. That was DNS essentially. There's no, yeah, Eric.
You mentioned the paper by Peterson recently.
Yeah, in water, yes.
And they maybe didn't look at internal waves, but they did look, I think, at surface waves.
Yeah. And they said,
You can correlate the two, or can you correlate?
no, there's no correlation. I wish there was. Oh my God, it would make the life a lot easier. But there's no indication by looking at the surface what the internal wave climate is. They were shocked that given the vigorous waves that break in, off that part of San Diego there, and there is a lot of surface wave energy, that there wasn't more mixing. And I'm going, why were you so? There's 30 to 35 meters of water depth there. The surface waves, you calculate the 1/E, decay of energy, and it's, you're down to 3 or 4 meters, and that's it. As colleague Ken Melville used to show all the time. So surface waves are not going to do it. They might if they just dump the stuff. Where it could be important is if they go sort of do the bad practice, which is simply just have an outfall that runs across the beach and then down the beach and into the ocean. There, actually, believe it or not, that's where the surface waves could be important. So going to the sophisticated approach, having an actual diffuser and putting it down lower is actually maybe not buying you anything. Maybe it's better to do the other way, except you wouldn't get permitted in California if you did that. So